Let's review standard reduction potentials. Many different half cells have been experimentally paired up with a standard hydrogen electrode and their potentials measured. These half reaction equations have been written as reductions and their potentials recorded in a table of standard reduction potentials. The extremes of the table are, at the top, fluorine being reduced to fluoride ion, and at the bottom, the lithium ion being reduced to lithium. We mentioned previously that on the reactant side of these reduction equations, fluorine is the best oxidizer. That is, it is very good at taking electrons, at oxidizing other things. That is, fluorine is itself very good at being reduced. On the other hand, at the bottom of the table, the lithium ion is actually the worst oxidizer. It is the worst at itself being reduced. It is terrible at gaining electrons. The same story can be seen if we look at the right side, the product side of these half reactions. The sign of the reduction potential indicates whether the atoms want to appear as they do as shown on the product side. In other words, this positive sign here suggests that fluorine would much rather be appearing as fluoride ion than as, on the other side, neutral fluorine. On the other hand, this negative sign in front of the reduction potential suggests that lithium is really not all that thrilled at appearing as neutral. It would much rather be what's on the other side, lithium ion. Let's determine the standard cell potential for the cell given by this equation. We're going to look up a couple of equations from the standard reduction potentials table, the reduction of copper 2 and the reduction of chromium 2. We're going to write down the values that we find in the table, and then we're going to think about a few things. From the given overall equation, we see that equation A, well, let's look at equation A. It's got copper 2 on the reactant side, and so does our overall reaction at the top of the screen. Therefore, equation A runs left to right as written. Its reduction potential remains unchanged. When we do something with the reduction potential, we're going to leave it as positive 0.34. In other words, equation A is what is happening at the cathode. The reduction happens at the cathode. What about equation B? Well, if equation A is the cathode, then equation B must be the anode. And the anode is an oxidation, which means that the equation that's shown, which is a reduction, actually runs backwards. And when we do something with the reduction potential, we're going to have to change the sign. In other words, we're going to flip this equation and we're going to flip that sign. What you do then to find the standard cell potential is you simply add the standard potentials of the two half reactions. We're going to leave the 0.34 the same. We had to flip the negative 0.91 to positive 0.91. We simply add those up and we get positive 1.25 volts. Turns out that things with positive cell potentials are galvanic cells. And galvanic cells, as we remember, have negative delta G values. A galvanic cell, which runs spontaneously, will have a positive E0 value. Determine the standard cell potential for the cell given by this equation. Again, we need to look up a few things in the table. These are both reduction values. We have here the reduction of iron 2 and the reduction of chromium 3. Given the overall equation, what about reduction equation A? We see here that in reduction equation A, we have iron 2 on the reactant side, and in the overall reaction, iron 2 is on the product side. Therefore, equation A runs backwards and when we use its reduction potential, we have to change the sign of it. In other words, the equation is flipped and the sign of the value that we pull from the table is also flipped. And when we flip something, that means that's the anode. Therefore, equation B must be the cathode. It runs left to right as it's written, and we don't need to change its reduction potential. What we're going to do is we're going to add up the two standard potentials. We're going to flip that first one to make it positive, and we're going to leave the second one as is. That gives us a value of negative 0.3 volts. Just like positive cell potentials were galvanic cells, negative cell potentials are electrolytic cells, which have positive delta G values. In order to make this reaction go, we have to supply an overpotential. We have to use external energy in order to make this reaction go. This reaction, shown at the top of the screen, will not go spontaneously if we just set it up. What about this one? A voltaic cell has the following half reactions. We have the reduction potentials, and we're asked to calculate the standard cell potential and write the balanced equation. Well, we have a hint here. Voltaic cell, which is a synonym for a galvanic cell. And we just learned that galvanic cells always have positive cell potentials. Therefore, when we add up some combination of these numbers, we have to come out with a positive value. If you follow the pattern that we've learned in the last two examples, you know that one of these values has to flip its sign, and then we add. Which of these two would you flip the sign for, such that when you add the results you would get a positive number? And I'm hoping you see that it would be that one. Similarly, that equation will be flipped. That will be the anode, and equation A, with the aluminum ion being reduced to aluminum, will be the cathode. So let's find the cell potential by taking negative 1.66 and then the flipped 2.9 number, so it will be positive, and that gives us a cell potential of 1.24 volts, which would be consistent with a voltaic or galvanic cell. And now let's write the balanced equation. We're going to expect the aluminum ion to be on the reactant side, just like it's written, the aluminum metal to be on the product side, just like it's written, but this barium ion is going to be on the product side, and this barium metal is going to be on the reactant side. So remember, equation B, involving barium, has to be flipped. You might think that that's balanced because we have one atom of each type on each side of the equation, but remember that the charges also have to balance. So we need to put 2 aluminums and 3 barium. That will allow the total charge on the left to be positive 6 and the total charge on the right to be positive 6 as well. Let's do one more. In acidic solution, will iron 3 spontaneously oxidize nitrogen monoxide to nitrate ion, or will nitrate ion oxidize iron 2 to iron 3 ion? Also, determine the standard cell potential. This term spontaneously means that when we're done, the cell potential must be positive. If we look up the equations from the table and their reduction potentials, we recall that one of these reduction potentials has to have its sign flipped. Which one must have its sign flipped such that when we add them we will still get a positive number? And that would be that one. Similarly, the equation that goes with that potential is going to have to be flipped in our overall equation. It turns out that iron 2 will be oxidized to iron 3 because the equation that is flipped is the oxidation. The standard cell potential will be negative 0.77 plus 0.96, which is positive 0.19.